Hello, you are listening to Pankaj Rai, and in this video we will be discussing the numericals of the chapter Current Electricity. Let us begin our discussion with the Wheatstone network. Now, to explain Wheatstone network, we'll first have to see about a cell and the potential difference. Okay, so let me take a cell. Let's say its potential is 40 volts. Okay, let me connect a wire. This is a positive and this is a negative terminal. Okay, now let's say that this is actually a plus 20 potential and this is a minus 20 potential. So the potential difference between them is plus 20 and minus of minus 20, so that would be 20 plus 20 and that would be 40 volts. So that's how a cell works. Now imagine that this wire is of a very high resistance material. Okay, so it is providing a very high resistance, so you can assume that this complete wire itself is like a resistance, as we have already seen in our previous standard that resistance is proportional to the length of the wire. So as and when the length is increasing, the resistance is increasing, and due to that the potential will be dropping. That is called as potential drop. Okay, to simply tell you, I can say that potential at this point is plus 20. By the time we check what is the potential at this point, the actual potential at this point, let's say it is plus 15, there has been a potential drop. Now moving ahead, let's say at this point we are having a potential of plus 10. Let's say by the time we reach here, let's say we are having a potential of 0, and as we move ahead potential keeps on dropping, so here we get a potential of minus 10. Moving ahead here, let's say we are getting a potential of minus 15, and here we are having a potential of minus 20. Okay, now let me check what is the potential difference between this point and this point. Okay, so for that I'll have to connect a voltmeter across these 2 points. So let's say I have connected a voltmeter across these 2 points. So this voltmeter will show me the potential difference between this point and this point. So that would be 10 minus of minus 10, so that will be 20 volts. So potential difference between these 2 points is 20 volts, and in the similar way you can measure the potential difference across any 2 points. Okay, now let us move ahead. Now let me join one more wire over here. Let's say I'm joining one more wire over here. Okay, so now as you can see that there are two wires which are connected in parallel between 2 points. Let's say this is a point A and let's say this is a point B. So there are two wires connected in parallel between 2 points A and B. Okay, for simplicity and for a good looking diagram, let me redraw this wire as well. Okay, let me erase it, and let's say this was the original wire. That's how we are habitual to see the two parallel resistances or parallel wires. Okay, now let us move ahead. Now potential drop, look, let us look at potential drop once more. This plus 20 plus 15 10. As we move ahead, let's say by the time we reach here we are having a potential of 0. By the time we reach here it is minus 10 minus 15 minus 20 and so on. Now the same potential drop would be there in this wire. So this is plus 20 plus 15 plus 10, and then again there will be a drop in potential. It will be 0, and there will be more drop. It will be minus 10 minus 15 minus 20 and so on. Okay, let me draw few more points. Let's say this is plus 10, and by the time we reach here the potential has dropped 5 points more, so it is plus 5. From 0, let's say this is minus 5, and moving ahead minus 10 minus 15. And about the next wire, plus 20 plus 15 plus 10, and let's say there is plus 5. Moving ahead this is 0, moving ahead this is minus 5, minus 10, minus 15, minus 20. So this is how these are the actual potential points. Okay, now as I've already told you, what if we want to know what is the potential difference between 2 points? So we have to join a voltmeter between them. Let's say I want to see what is the potential difference between these 2 points. So I'll join a voltmeter between these 2 points. So these points are having potential of plus 5 and minus 5. So difference between them is 5 minus of minus 5. That would be 10 volts of potential difference. Okay. Now let me take some other point. Okay. I can even take points between the two wires. Okay. Let's say this is plus 5 and I am connecting a voltmeter between these 2 points. Okay, so there is a voltmeter. Now this voltmeter will give me a reading of plus 5 minus of minus 5. So the potential difference between these 2 points is 10 volts. So in this way you can measure potential difference between any 2 points. But wait, what happens when I join a voltmeter between these 2 points? The voltmeter will give us the potential difference. This is plus 5, this is also plus 5, so difference between them is 0. So voltmeter will give us 0 volts between these 2 points. That means these 2 points are at same potential, so that's why the potential difference between them is 0. Similarly, potential difference between these 2 points will be 0, and potential difference between these 2 points will also be 0. Okay, now as you know that let's say there is a potential, as you know that if there is zero potential, that means there is almost no cell or no battery. So if I join a wire between, let's say, these 2 points, now these 2 points are equipotential, there is zero potential difference between them. So if I join a wire between these 2 points, there will not be any current flowing between these 2 points in the wire. So that's what we call as equipotential points. And what if I join a galvanometer over here? Obviously, if no current is passing because the potential is 0, so galvanometer will show no deflection, and that is called as null point deflection. Let us move ahead. Let's say I take these 2 points as point C and point D, okay, and I try to connect a wire between them. As we know that these are equipotential points, so potential difference between them is 0, and there won't be any current passing through them. So current across them will be 0, and galvanometer will be showing no deflection. There won't be any deflection in the galvanometer. Okay, now let us try to study this condition. This is called as balanced condition of Wheatstone network. Okay, this is happening because the potentials are equal. Potentials are equal because potential drop from 10 to 0 and 0 to minus 10 is same as potential drop 10 to 0 and 0 to minus 10. Now potential is dropping because of resistance. Okay, so I can say that resistance from point A to C and C to B, A to D and D to B, they are exactly same. That's why the potential drop across them is same, 10 to 0, 0 to minus 10, 10 to 0, 0 to minus 10. So potential drop across all the resistances AC, CB, AD and DB, they are same. So I can say that all the four resistances are exactly same. Okay, so I can say that, let's say this is R1, let's say this is R2, let's say this is R3, and let's say this is R4. So I can say that R1 is equal to R2 equal to R3 equal to R4. That's why these 2 points are equipotential. Okay, so this is one of the special case where the resistances are equal. Okay, now what happens when resistances are not equal? Okay, so let us take that example. Now let me just remove this wire. Okay, I'll replace it with another wire. All right. Okay, let me remove the galvanometer as well for now. Okay, now let me introduce one more wire. Let's say this wire is quite lengthier than the previous wire which was joined. Okay, So as you know that resistance is proportional to length, so resistance across this wire will be much more. Okay, so let's say what do I mean by that is the drop in potential would be there, but it would be not exactly same as from A to C. Let's say A to C is, let's say, 10 centimeter. So in 10 centimeter we were getting a drop of 10 volts. So now let's say from A to, let's say, this point. Okay, let me say that this point is D. Okay, now let's say A to C is 10 centimeter. All right, now let's say there was a potential drop of 10. Now let's say A to D is let's say 20 centimeter. Okay, so potential drop would be something like this. Okay, let me write down. Okay, let's say from 10 we are coming over here, so we are getting a, let's say, till the point we reach here we are getting a potential of plus 5. Till the point we reach here we are getting a potential of 0. Till the point we reach here we are getting a potential of minus 5. And till the point we reach here we are getting a potential of minus 10. Okay, now the potential drop per unit length is different, which is called as potential gradient. Okay, now in this case in 10 centimeter only we were getting a drop of 10, and in this case in 20 centimeter we are getting a drop of 10. So potential gradient is different. That is altogether a different topic. Potential gradient is the drop in potential per unit length. But here we know that resistance of AC is less than resistance of AD, because length of AD is more, so this resistance will be higher. Okay, now but the potentials will be dropping from 10 to minus 10 and 10 to minus 10 in the same way. So obviously there will be points which will be equipotential, like this point C and D. If I connect a voltmeter between these 2 points, again the potential difference between them will be 0. Again there will be more points like this one and this one. Between them the potential difference would be 0. Okay, so what if I connect a wire between this point, okay, and let's say I connect it, let's say, over here. Okay, so what happens now? This point might be having a potential of, let's say, 0, minus 1. Let's say this is having minus 2. So potential difference between 0 and minus 2, there will be some potential difference of 2. So there will be a flow of current. Okay, so let's say my wire is connected over here and I am trying to connect this wire over here. So there will be current passing through it because there is a potential difference. But what if I keep on testing that is there some point to which if I connect the current stops flowing? Yes, there will be a point. If I connect this point with this point, when I connect these 2 points, then if I am having a let's say galvanometer here, it would be showing a 0 deflection. So this will be called as null point. Okay, null point or 0 deflection. So now what is happening? Because the potential drop are same, 10 to 0, 0 to minus 10, 10 to 0, 0 to minus 10. Okay, but resistances are not same. That is the thing to understand here. Let's say this is R1, R2, let's say this is R3, this is R4. So in this case I can't say that R1, I can say that R1 is equal to R3, R2 and R3 is equal to R4, but I can't say that R1 is equal to R3. But what I can say is, what is the ratio of R1 is to R2 is same, which is the ratio of R3 is to R4. So I can say that R1 upon R2 is same as R3 upon R4, or I can also reiterate it as R1 upon R3 is same as R2 upon R4, and that is called as the condition or the balancing condition of the Wheatstone network. Now you are having pretty diagrams in your book to which you can refer to see how exactly the diagram of Wheatstone network is, but this is how it works. Okay, so we get that R1 upon R2 is R3 upon R4, or R1 upon R3 is R2 upon R4. The resistances are in ratio, or they are proportional. Then and only then we get a null point. Now what about the numericals? Numericals are very simple. Okay, now they ask you something like that there are 4 resistance, 5, 10, 15 and X, which are connected in series to form a Wheatstone network. Something like, let's say this is the first one, let's say this is the second one. Okay, continuation, that is in series, this is the third one, and continuation series, this is, let's say, the fourth one. Okay, so this is 5, this is 10, this is 15, and this is x. Now they say that the condition is balanced according to the Wheatstone network. So the question is, that is this point and this point, when there will be a galvanometer here, so it would be showing no deflection, so that is called as a balancing condition. And at that point of time we have to find what is x. It is so simple. Let's say we name it as r1, r2, let's say this is r3, let's say this is r4. Okay, now let me do one thing. Let me write r1, r2, and r3 and r4. Okay, so r1, r2, r3, r4, because they were in continuation and in series, so I named them this way. Now make sure that you do not use this formula over here, because here I have changed the name. What you have to remember is the ratio to be taken. Okay, ratio has to be taken of the adjacent resistances. That is, in this case I can say that r1 upon r2 is same as r4 upon r3, or I can also say that r1 upon r4 is same as r2 upon r3. In either of the cases we have to substitute the value. Let's say we do that. Let's say this is r1 is 5, r2 is 10, then the r4 is x, and r3 is 15. So let us take 15 here. So we'll get 5 times 15 upon 10 is x. So 5 times 15 is 75. 75 upon 10 will be 7.5. So the unknown resistance x is 7.5 ohms. Let me take one more very special solved example of your book. Now this is very interesting numerical. Okay, what we have been given is, we have been given that there are 4 resistors which are, let's say, P10, Q15, R25, and S, which is 50. Okay, and they are connected in series in the arms, which are AB, BC, CD, and DA respectively of a Wheatstone network ABCD. So let me make a Wheatstone network ABCD. Let's say this is AB, let's say this is BC, let's say this is CD, and let's say this is DA. So this is A, B, C, D. Let me replace the wires with resistors. Okay, so these are the resistors which are given in the numerical. Okay, now this is P, which is, let's say, 10, this is 15, okay, this is 25, and this is 50. All right, now this is a Wheatstone network, so let me complete it. It would look something like this, and obviously there will be a flow of current in this wire. Okay, but except if I join these 2 points, there won't be any current. Okay, but let me check. Am I sure that there won't be any point? Because they have given the 4 resistances. Let me check first of all whether they are satisfying the balancing condition or not. Let me check that is 10 by 50 is equal to 15 or 25 or not. So 10 by 50 is 1 by 5, and 15 by 25 is 3 by 5. So they are not equal. That means B and D, they are not equipotential points. So obviously there will be a flow of current in this wire. Okay, so this is not a balancing condition. So what is the question which has been asked? The question is, we have to find that what resistance we have to connect in parallel to this resistor, which is S. Okay, question is, what resistor we have to connect in parallel to S to balance the network. Okay, now what I am saying is, question can be asked in any way. Okay, now these are the 4 resistors which are given in a Wheatstone network which is not balanced. So we have to adjust either of the resistors to make the network balance. Okay, so we have to see that what changes we have to make. For example, let's say this is 10 by 50, which is 15 by 20, which is not equal to 15 by 25. But if let's say I have to make it, okay, so this is 3 by 5. Let's say I make this one as well as 3 by 5, so it will be like 30 by 50 is equal to 15 by 25, so it will be balanced. Okay, so if I want to balance this network by changing this resistor, so I have to replace this 10 by 30. Okay, but I cannot replace, so let's say I can increase the resistance by including one more resistor in series with this 10. Okay, something like let's say in place of 10 I'm this is 10, which is usual. I'm introducing one more. Let's say this is 10 and this is 20. So now the series total will be 30. So 30 upon 50 will be same as 15 upon 25. So it will be balanced. So the correction to be made in this is that we have to connect a resistor in series, which is 20. Okay, but this is not the question which is asked. The question is asking that we have to change this one. Okay, and they are also mentioning that we have to connect something in parallel. But even if they do not mention that we have to connect in parallel or not, we can find it out. Okay, let's see how to do this numerical. Okay, now let me name that. Let's say this is R1, this is R2. Okay, and let's say this is R3, and let's say this is R4. Now we do not have to change R1, R2 and R4, that is we have to change R3. So let us consider that we are not having this. Okay, so consider that we are not having this. So what if we have to find this? Okay, so we can find it by using the formula that R1 upon R2 is same as R3 upon R4. Okay, so by that we will get that R1, which is how much? R1 is 10, R2 is 15, R3 we do not know because we have to find what should be the value for the network to be balanced. R4 is 25. Okay, so R3 will be 10 times 25 upon 15. That would be the value of R3. This will get cancelled. Let's say this is going in 5 and this is in 3, so it is 50 by 3. So R3 has to be 50 by 3, but it is given as 50. I have to reduce it. Okay, and we know that to reduce the effective resistance we have to connect something in parallel. That's why the question asks that we have to connect in parallel. Even if it would have been asked, we can find out that to reduce R3 from 50 to 50 by 3 we have to connect something in parallel. So let us connect something in parallel to R3, I mean to 50. Okay, so in 50 let us we are connecting something in parallel, let's say, which is X, and the effective of 50 and X should be 50 by 3, which will be complete R3. Alright. Okay, now first of all, this is not R3, this is 50. Let me just delete the R3 from there to remove any confusion. Okay, now this is 50, this is X. Okay, so I have to find out this X, which when connected in parallel with 50 will give me the complete resistance of this arm as 50 by 3, in which case the network will be balanced. So it is a very simple equation, as we know that I can write as 1 by R3, which is the effective resistance of parallel, should be equal to 1 by 50 plus 1 by X. It is so simple. Okay, so I have to find X because I know R3 already. 1 by R3, 1 by R3 would be 3 by 50 equal to 1 by 50 plus 1 by X. Let me take it here. So 3 by 50 minus 1 by 50 equal to 1 by X. So 3 minus 1, that will be 2. 2 by 50, so 2 by 50 would be 1 by X, so that will be 1 by 25. So I am getting that X is equal to 25. That means if I connect a resistance of value 25 in parallel with this 50, the effective resistance of arm AD will become 50 by 3, and which will balance the Wheatstone network. So in this way you can solve any numerical on Wheatstone network. Thank you very much.